It's a great pleasure to introduce Benjamin Linowitz from Oberlin College that will talk about mutually spectral Riemannian manifolds. Go
So, thank you very much for the invitation to this wonderful session. So I want to talk about families of isospectral manifolds. And so there are really going to be two parts to this. I'm going to focus on surfaces, so hyperbolic surfaces to start with at least. And so the question is, I want to study the maximum cardinality of a family of pairwise isospectral non-isometric surfaces. And so, you can look at, say, surfaces of genus G, and then you really get two questions. Question one would be, what's an upper bound for the number of isospectral genus G surfaces you can produce? And question two would be to actually try to find a lower bound, meaning how big of a family of genus G surfaces that are isospectral can you actually construct? So part of the reason that I want to stick to surfaces is because besides one, they've been studied more classically for this problem, but also it's only for surfaces that you can come up with an upper bound that's better than saying isospectral manifolds have the same volume, the number of manifolds, hyperbolic manifolds with a fixed volume is finite, therefore isospectral families are finite. So it's only in the surface case that you can do better than this. And so I just want to go over some basic things about surfaces. So to start with, I want to talk about what's called the pants decomposition. So a pair of pants, it's a 3 times punctured sphere. It's called a pair of pants for an obvious reason when you draw it this way that I did. So the classification of surfaces implies that every orientable surface, and I'm thinking of the surface as being closed and connected, is topologically either a sphere or it's the connected sum of tori. So if the genus is at least 2 in a surface, then I can cut the surface along simple closed curves in order to decompose the surface into pairs of pants. And so in general, this isn't unique. Like here are 2 different ways of doing this for genus 2 surface, but if we cut along here and here, then on each side, we're going to get a pair of pants that we've kind of glued together along the waists. So conversely, given any 3 positive numbers, there's always going to be a unique hyperbolic pair of pants with cuff lengths equal to those 3 numbers. And by cuff length, I just mean, so each of these cuffs is going to become a geodesic in the surface. And so if I want to produce a pair of pants with 3 arbitrarily chosen lengths for the cuffs, what you do is you just take a pair of hyperbolic hexagons, and then you glue them along 3 of the edges, and you make the other edges of lengths 1, 2, and 3. Now, so when we have our pairs of pants, an appropriate number that we're going to glue together, in order to specify our surface, we have to give lengths to all of the cuffs. But then there's this issue that when you're gluing together 2 cuffs, like at those circles, you can do like a twist before you glue together. And so you get this twist parameter also. And that's just measuring the twist you do when you glue together the cuffs. So when you've specified all of these, meaning the pants decomposition, the cuff lengths, and the twist parameters, then you've specified your hyperbolic surface. So this way of parameterizing hyperbolic surfaces, these are called like Fenchel-Nielsen coordinates. And so it's this nice fact that Pants decompositions correspond to finite graphs that are 3 regular. And here's the idea. Let's say, and I'm just going to draw a quick 3 regular graph. There we go. So here's how you get a Pants decomposition out of this. At each vertex, I'm going to draw just a pair of pants. All right, so that's 1. This is number 2. This is 3. And here's 4. And so I'm going to glue those together, these together. And then when you do this, you see that you get a genus 3 surface. And so this is the idea of how to go back and forth between finite graphs that are 3 regular and surfaces. So here's a theorem. It's proven in Boozer's book on compact surfaces. It says, if S is a compact hyperbolic surface, there are only finitely many other surfaces which are isospectral to S. And so I want to sketch the proof of this. And so the idea of the proof in broad strokes is going to be, we're going to construct a surface S prime that is isospectral to S. And we're going to see how many that there are only finitely many possibilities for all of the choices we have to make. And so just note that the genus of any 2 isospectral surfaces is the same. So the first factor we're going to use is the Selberg trace formula. It implies that Laplace isospectral surfaces are length isospectral, meaning they have the same set of lengths of closed geodesics. So in particular, every time I need to choose a length of a closed geodesic on S prime, I can only choose lengths that occur in the length spectrum of S. Fact 2 is called Bers's theorem. It says that a genus G surface has a Pants decomposition, all of whose cuff lengths are less than some constant B sub G. So it's some constant that depends on the genus. And there are actual concrete bounds for B sub G that are known. So if I'm trying to construct S prime, this is a surface isospectral to S, then I know that, well, I'm going to have to specify cuff lengths at some point. Those cuff lengths, they can be taken to be less than this Bears constant. And, well, there are only finitely many closed geodesics with bounded length on S. Therefore, when I choose the cuff lengths for S prime's Pants decomposition, I only have finitely many choices. So let's put all this together. I'm constructing a surface S prime. It has to have the same genus as S, and there are only finitely many 3 regular graphs with 2G minus 2 vertices. So that's finite. Now I get my Pants decomposition. There are only finitely many choices for the cuff lengths because there are only finitely many geodesics of length less than the Bayes constant on S, and our surfaces are going to be length isospectral. And if you do some hyperbolic trig, then you can prove that we get only finitely many choices for the twist parameters also. So something that's nice about that proof we just gave is that all of those statements that such and such is finite can be made explicit, that we can come up with actual bounds for the Bayes constant, the number of finite three regular graphs, the number of geodesics on a hyperbolic surface with bounded length. You put all of this together, and what Boozer concluded was, if you have a closed hyperbolic surface, genus G, then there are at most e to the 720 g squared surfaces that are isospectral to S, but not isometric.
Gentlemen, and if the surfaces are isospectral, will the graphs be isospectral for the combinatorial Laplacian or not necessarily?
I've never thought about that. I'm not sure off the top of my head. I'm sorry.
Okay, thank you.
Yeah, so the 720 is not at all best possible. That can be improved. On the other hand, the e to the g squared, the g squared there, that can't be improved if you use the same parameterization as Boozer. That's kind of as good a bound as this method will give you. And that's part of the reason that we had to wait almost 25 years for a substantial improvement of this. So this is a relatively recent result of Hugo Parlier, I believe a student of Boozer. And he was able to change the e to the constant g squared to e to the constant g log g. And the idea of his paper is he had to come up with a completely different way of parametrizing hyperbolic surfaces. And in particular, he wanted to come up with a way of parametrizing surfaces using geodesics that are as short as possible. So this is sort of state of the art for right now in terms of upper bounds for the size of an isospectral family of surfaces. So now I want to tell you about some work that's been done in the other direction, and this is actually constructing large families. So first, I just want to say a little bit about what's called Tsunada's method. I'm sure it's familiar to many, maybe most of you. So essentially 99.99% of papers that construct isospectral objects use in some form or another, a result of Tsunada. And so the idea is, if you have a group G that's finite and subgroups H1 and H2, you call them almost conjugate if every conjugacy class in your bigger group G intersects each of the subgroups the same number of times. So for instance, if two subgroups are conjugate, then they're trivially almost conjugate as well. And so kind of the game is to find almost conjugate, but non-conjugate subgroups. So the result of Tsunada is, if M is a Riemannian manifold, finite group G acts on it by isometries. If H1 and H2 are almost conjugate subgroups, then the quotient manifolds are isospectral. An equivalent statement, which I personally find a little easier to think about, is if you have a surjective homomorphism from the fundamental group of M to your group G, then the covers you get by pulling back the two subgroups are isospectral. Now, so this part, constructing the isospectral manifolds in this way tends to be pretty straightforward. In practice, what's often the hardest part is proving that these manifolds that you just constructed that are isospectral, that they're not isometric. The setting, I mean, it just tells you that these isospectral manifolds, they're not conjugate by an element of G, but you still have to check the larger isometry group of your, say, universal cover. And so that in practice is where a lot of the work comes in. And so Brooks, Gornet, and Gustafson, and you have no idea how difficult it was to find that photo of Gustafson. So proved the following. There exists an infinite sequence, G sub I, of positive integers such that for each I, there are at least e to the log G squared isospectral, non-isometric hyperbolic surfaces. So remember, and these obviously are going to have genus G sub I. So the upper bound of Parlier is like e to the G times log G. The maximum size of these families is like e to the log G squared. And so there's still quite a bit of difference there. So these surfaces, to construct them, they used Tsunada's theorem to produce a very large family of almost conjugate subgroups from certain finite Heisenberg groups. And to date, there aren't any known constructions of large families that get this big, that don't use Tsunada's theorem with Heisenberg groups. Like, I think it'd be an interesting question just in group theory to try to sort of classify which finite groups contain the largest number of almost conjugate subgroups relative to the order of the group. So these are surfaces. In 2009, Ben McReynolds extended this to hyperbolic N manifolds and certain complex hyperbolic manifolds as well. So Ben proved that there's some constant C such that the maximum cardinality of a family of isospectral, non-isometric, volume X hyperbolic manifolds, it's at least e to the constant log X squared. And so Ben also used Heisenberg groups, and he got sort of this same growth factor. All right, and so I want to end by talking about a result of mine from 2017 with Misha Belalipetsky. And so we proved that if H is a simple Lie group with rank at least 2, then the maximum cardinality of a set of isospectral H locally symmetric spaces of volume X, it grows like at least as fast as X to the log X over log X squared. So one really interesting thing about this bound that we got is that it comes extremely close to the actual bound for the number of lattices, so the number of H locally symmetric spaces with volume X, meaning there are approximately X to the constant log X volume X H locally symmetric spaces. And so if you could get rid of this log X squared factor, then this would sort of be telling you that a large proportion of all locally symmetric spaces with a certain volume belong to isospectral families. In fact, at the end of our paper, we give this, it's a number theory problem involving class field towers. And we're able to show that a positive resolution to this number theory problem would actually allow us to get rid of that log X squared factor. And so maybe I'll end by just saying that, in fact, the hypothesis in our theorem it's a little bit more general than this simple Lie group with rank at least 2. We're able to prove the same thing for non-compact semi-simple Lie groups as long as they don't have simple factors of type A1. So I'll end there. Thanks very much.
Hi, Ben. Are there any other questions?
So how do, I mean, so the number theoretic problem you're talking about, I mean, class field towers,
Yes.
this is probably related to the, I mean, this is related to the covers here somehow, but how close is it? I mean, do we have time for you to say something about it, or should we just read the paper? I guess it's probably a question to the organizer.
No, I can say what the gist of the problem is. So a class field tower, it's, let's say we use totally real fields. So it's just a sequence of totally real fields with, okay, they have the property that 1, so their discriminants go to infinity. But when you normalize by taking the discriminant to the 1/degree power, so that turns out to be constant. What we need in our proof is to be able to construct lots and lots of lattices that we know are not going to be isometric to each other. And what we need is, we need a sequence of number fields. The degree needs to go to infinity. The root discriminant needs to be uniformly bounded. And we need a prime that is very close to being inert in all of the different fields. And so it's impossible in an actual class field tower to have a prime that's inert in all of the extensions. But that's what we need, some sort of variant on the class field tower construction with primes that gain a lot of inertia in the different fields. And if we had such fields, that would feed into our construction of these lattices, and it would give us enough lattices to get rid of that log X factor.
Thank you.
Okay, we have time for one short question more. Okay, if not, we thank again to Benjamin.